Hello, my name's Joel Johnson, and I'm going to talk today about a research project that I've been doing over the last few years, looking at using infrared spectroscopy to measure bioactive compounds in some Australian pulse crops. And I'm from Central Queensland University here in Queensland in Australia. So the Australian cropping industry is quite a big industry in Australia, had a value of over $28 billion in 2020. Those figures are from just 2 years ago. And it's the second largest section of the agriculture sector, which is just behind the livestock industry in value. And around 3/4 of all of our total crops grown here in Australia are exported every year. That figure in the middle of the screen just shows some of the main produce. So you can see there's wheat, other grains, pulses, canola, sugarcane, some of the main crops that we grow here. So this figure here just shows some of the land use of Australia. So there's quite a lot of grazing of native vegetation, particularly in the drier areas of Australia. See up towards the centre and the north especially, some grazing of modified pastures. And there's quite a lot of cropping done in the southern regions along the south and eastern coasts, and that's where most of our crops are currently grown. There is work being done looking at expanding the cropping sector in Australia further northward, so along the northeast coast and especially up along the northern regions along Western Australia, Northern Territory and Northern Queensland. A lot of that work's being done by the TRC for Northern Australia and a few researchers from around Australia, so working on this. But I'm here to mainly talk about the Australian pulse crops. So these include things like chickpeas, fava beans, mung beans, lupins, lentils, and field peas. So I've got them listed down the bottom of the screen in the order of abundance. So lupins, chickpeas, and field peas are the main ones, with other levels of lentils and fava beans, and only a few mung beans that are currently grown. But all up, the pulse crops comprise around 10% of all cropped area in Australia. So that includes grains, horticulture, forestry, all that sort of thing. So the main benefits of the pulse crops are, for the farmer, it fixes nitrogen into the soil, so it's good for a rotation crop. And for the consumers, they're high in protein, high in other minerals, and other health benefiting compounds that have quite a good nutritional benefit. So we harvest over 2.5 million tonnes of pulses every year. Again, most of this is exported, over 75% is exported. And we had $1.2 billion worth of exports. That figure's from a few years ago in 2015. As I mentioned, the health benefits of pulses are quite abundant. So they're a great source of protein, also a good source of vitamins and minerals. And they also have a low glycemic index, which means that they can be consumed by people with diabetes without causing postprandial hypoglycemia. And they also contain more phenolic compounds than other grains, which provides them with a wide range of health benefiting effects, including their higher antioxidant activity, improving cardiovascular health, lowering blood pressure, reducing the risk of cardiovascular disease, also reducing inflammation and reducing cholesterol levels. They also have potential anti-cancer effects. And overall, this means they can be classified as a functional food product. So you might be asking, what is a functional food? So a functional food is basically a food which has health benefiting effects more than its basic nutritional value. So as I mentioned, those include things like cardiovascular benefits, potential anti-cancer effects for pulse crops specifically. And market research has demonstrated that consumers will pay 10 to 40% price premium for these functional foods which have demonstrated health benefits. And the international market for functional foods and nutraceuticals is actually worth over $170 billion. So there's great potential for Australia to tap into this massive market. However, we need to be able to demonstrate that these levels of health benefiting compounds are present in all the crops being sold. So that calls for a routine quality assessment of these bioactive components before we can market them as functional foods. So there's a range of analytical methods available to measure these bioactive compounds, mainly phenolics and antioxidants I'll be talking about in this session. And these include colorimetric methods, high performance liquid chromatography coupled with mass spectrometry, and for volatile compounds, gas chromatography coupled with mass spectrometry. However, these methods can be expensive and time consuming. They also require trained personnel. And they also require destructive extraction processes. So they're a destructive form of measurement, and many of them use large amounts of chemical solvents as well. So we're going to talk about infrared spectroscopy here. So as many of you attending this session will be aware, infrared spectroscopy, or IR spectroscopy for short, is an emerging method which is non-invasive and uses infrared light to look at the chemical bonds within the sample. And based on this, we can determine what the composition of the sample is from a qualitative aspect, and also from a quantitative aspect, depending on the relative abundance of the different types of bonds. So the main benefits of infrared spectroscopy are its speed. It only takes a few seconds to measure a sample in most cases. It's non-destructive. There's really no ongoing costs. Many instruments are portable, and it can also provide, you can also analyze samples through the container in some cases, depending on the sample type and the analyte. And again, this means that it's much faster than other analytical methods because you don't even have to take it out of the container. You can just scan through the container and get a measurement. So the two main types of infrared spectroscopy of interest are near infrared and mid-infrared spectroscopy. So NIR between 750 to 2,500 nanometers is the most commonly used in food industry. However, I also looked at mid-infrared spectroscopy in my research. So that's between 2,500 to 25,000 nanometers. There are some drawbacks to infrared spectroscopy. They're not as specific as traditional analytical methods. So they're really only good for measuring analytes which are present in high concentrations. Typically more than 0.5% can be readily detected by NIR. Analytes with lower concentrations are much harder to detect. And there may be interfering compounds present. In particular, water absorbs a lot in the NIR and MIR regions. So the moisture content of the sample can interfere with the measurement of other analytes. They also require robust calibrations, which are developed on many samples. So we're talking more than 50 samples in most cases. And that can be quite expensive to initially analyze that large number of samples to create a robust calibration model, which you can then use to predict the content of new samples. And there is also a challenge in ensuring representative sample presentation when using mid-infrared spectroscopy, which is one of the drawbacks to that method. So in my research, I was looking at using infrared spectroscopy to predict analytes in Australian pulse crops, so fava bean, wheat, mung bean, and chickpea. And I was specifically looking at total phenolic content, total antioxidant capacity, and a few other analytes depending on the crop, usually protein and anthocyanin content. So a general overview of the methods here. So the pulse crops were ground, and then I used a reflectance near infrared spectroscopy with a rotating sample cup and integrating sphere, and also FTIR spectroscopy on the same samples using a Bruker Alpha 2 FTIR on the powdered samples. And then after that, these samples were analyzed for total phenolics, and that should be antioxidant capacity, not capsaicinoids, apologies, using colorimetric assays and also HPLC to confirm the phenolics present. And then chemometric analysis was conducted to predict these analytes. So I'll briefly talk on each of the crops separately. So fava bean is quite a significant crop in Australia. So we're the third largest exporter of this crop around the world. And fava bean is well known to have high levels of phenolics and antioxidants, which can provide it with quite high health benefiting effects. So we looked at 100 different samples comprising 10 varieties grown across 2 seasons and 2 locations. So we split this into 60 samples for model development. So that was all from 1 season. And then the following season, we had 40 samples, and that was used as a independent test set. So the total phenolic content and antioxidant capacity were measured using colorimetric assays. And that's true for all of the samples, all of the sample types that I'll discuss. So looking at the NIR spectra, we can see quite a lot of chemical information there, particularly bonds from moisture, so around 1936 nanometers, structural carbohydrates, so all those CH bonds and starch in there. So we've got the second overtone, first overtone, and then combination bands for the CH, CH2, CH3 bonds. And also protein showing up around the 2100 to 2200 nanometer region as an amine bond. The mid-infrared spectra is a little bit more complex. However, most of the bonds responsible for these peaks, once you break it down, is actually similar to what we saw in the NIR. So sort of working from left to right, you can see there's no moisture. We've got some peaks from structural carbohydrates or maybe lipids. And then there's peaks from starch, the amide, and then cellulose ring again. So look at the prediction of total phenolic content. We found quite good prediction using near-infrared spectroscopy, the cross-validation R squared of 0.88 and RPD of 2.9. Slightly poorer results in the independent test set, which is usually expected because this test set is drawn from a completely different set of samples to the calibration set. So in this case, it was a different growing season. However, there's still reasonable results found in this test set. Particularly, they'll be quite fine for discriminating between samples with high or low total phenolic content. So potentially not giving the exact quantitative value, but sort of screening, making sure that the total phenolic content is above a set of cut-off lower value. So all the samples that were above that value could then be sold as functional food. So we found poor results using mid-infrared spectroscopy. So an R squared of 0.37 is quite low predictive power. And I've got all the results, model results in the table at the bottom of each slide if you're interested in the specifics. So when we look at the loadings plot for total phenolic content, we saw peaks matching amide bond, so from protein, and also CH-OH bonds, which are most likely due to the structure of the polyphenol group, which is like a benzene ring with an OH group coming off. So that's got plenty of CH bonds all around it and an OH bond. We believe that's the main contributor because polyphenols obviously are specific to phenolics. But there also seems to be some correlation between the protein content and total phenolic content of samples, which is why the amine bond is showing up in the second principal component of the regression. So I should probably mention all of the analysis was done using partial least squares regression, or PLSR. And these bonds were quite similar to those found by previous authors in other crops. So again, in fava beans, looking at predicting the antioxidant capacity, we had slightly poor results compared to total phenolic content. but again, still reasonable for predicting high or low content of the samples, and fairly poor results using mid-infrared spectroscopy, so no predictive power there. For the antioxidant capacity loading plots, we found almost identical loading plots compared to the total phenolic content. As you'll see here, these two graphs are almost indistinguishable, which indicates that both these methods are measuring the same analytes, which makes sense because there's a very strong correlation between the total phenolic content and antioxidant capacity. So Pearson R value of 0.92, which essentially means that all of our antioxidant capacity in the farbamine is coming from phenolic content. So this NIR model appears to be indirectly predicting the antioxidant capacity from the total phenolic content, which it can pick up through those OH, CH, and the amide bonds. So looking at other analytes, we found excellent prediction of near-infrared spectroscopy, and that has been previously reported. The prediction of protein has been previously recorded by previous authors, although our model performance was slightly better than any previous literature. However, we're unable to predict several other analytes which we looked at, including the anthocyanin content and vicine and convicine content. So those last two compounds are anti-nutritional compounds which can reduce the digestibility of farbamine. So there's an interest in trying to breed new varieties with low levels of these compounds. However, we found that in this case, the near-infrared spectroscopy couldn't predict these analytes, which is likely due to the lower levels of these compounds. So we're looking at less than 0.1% for most of these analytes, which is quite hard to pick up using infrared spectroscopy. So another thing we looked at in the farbamine flower was predicting the protein content when we collected the spectra through a Ziploc bag. So if you can see the photo in the top right corner, that's collecting the NIR spectra with a fiber optic probe through a Ziploc sample bag, and the farbamine sample is in the bag. And notably, we found there was still reasonable accuracy for the prediction of protein content. So an R squared of 0.67 the cross validations that's shown in the right figure, that scatter plot on the right. So this indicates that we can quickly measure the protein content and maybe other macro analytes that are present at high concentrations without having to remove farbamine samples from their storage bags. This could be useful for when you're working through a large number of samples, just quick quality assurance. Again, it's not going to give you as accurate results, but it's quite interesting that we can predict protein content with acceptable accuracy, even when the spectra is collected through the sample bag. So wheat is the next crop I'm going to talk about. It's not a pulse crop, but I included it in this study because it is the most widely grown grain crop in Australia, and quite economically significant from that aspect. It also contains low levels of phenolics compared to most pulses. So it was chosen as a matrix to test the performance of infrared spectroscopy at lower levels of phenolics and antioxidants. So we got 65 samples of wheat from the Australian Export Grain Innovation Centre, and these encompassed a range of different varieties and grains of wheat. And some of these samples were pearled, so the outside layer was removed to provide a range of different phenolic contents. So the pearled samples would have lower levels of endosperm and thus lower phenolic content. So the prediction of total phenolic content, we found quite good results using both near-infrared and mid-infrared spectroscopy. So we've got the graphs for near-infrared spectroscopy on the top left. A and B are the calibration set and the test set. And then on the right side of the screen, the graphs there are the prediction of phenolic content using mid-infrared spectroscopy. So for the test set, we've got an R squared of 0.83 using NIR, and 0.73 using MIR, which is quite good. And again, when we look at the loadings plot, we found that the amine bonds and ROH bonds, so again, that potentially from polyphenol groups, were the main compounds contributing to the predictive power of these models, which indicates that inference spectroscopy is picking up the right analyte. So for the prediction of antioxidant capacity, found slightly better results compared to farbamine, so using near-infrared and mid-infrared spectroscopy again. So an R-squared of 0.88 for both NIR and MIR in the calibration set, and approximately comparable values in the test set. So finally, we looked at predicting the protein content of the wheat, which gave excellent results using NIR, so 0.99 for the R-squared value in the test set using near-infrared spectroscopy, and quite good results using mid-infrared spectroscopy as well, so R-squared of 0.93 in the test set. So this indicates that near-infrared and mid-infrared spectroscopy can accurately predict our protein content as well as other bioactive analytes, so the total phenolic content and antioxidant capacity in wheat, which is quite a significant step forward in this field. So mung bean is a fairly minor crop, as I mentioned in the introduction, so it only comprises about 5% of pulse production in Australia, but there is potential to expand our growing regions into Northern Australia, and there's quite a bit of research going into that. So 90% of the crop is currently exported. The industry value is around $100 million. So there's growing interest in its anti-inflammatory and cardiovascular benefits, and it's viewed as a health or medicinal crop in the international market. So in China, it is seen as a way of cooling the blood, which is that way of recognizing the health benefits of the crop and other nutritional benefits. So I looked at 100 different samples from 5 varieties, which were grown in controlled field trials in North Australia. So for the prediction of phenolics and antioxidants, we found fairly poor results. So there was some predictive power in the, particularly in the cross-validation for the antioxidant capacity. So that's FRAP in the top row of these tables, but really no predictive power in the independent test sets, which indicates that neither of these techniques, so NIR and MIR, weren't able to pick up the phenolics or antioxidants in these crops. We also trialed another measure of antioxidant capacity to confirm the results. So that's the second entry in these tables, so cupric reducing antioxidant capacity. However, we found basically the same results. The inference spectroscopy wasn't able to predict the antioxidant capacity in the mung bean, no matter which analytical method we used to measure the antioxidant capacity. So this may be due to increased complexity in the matrix, so other analytes obscuring it, so other non-target constituents, or it could be due to the lack of sufficient range of the phenolic or antioxidant capacity to be able to create a predictive model. In other words, all the samples were relatively close, relatively similar to each other, so it's very hard to create a predictive model. So the final crop I looked at was chickpeas, which is one of the larger pulse crops, the 20 to 35% of pulse production, and most of that is DESI type chickpea, which I investigated in this work. Australia is the largest exporter of chickpea in the world, value of about $1.3 billion in exports every year. And there is increasing interest in its health benefits, such as cardiovascular benefits, and also potential anti-cancer properties. So I looked at 97 samples, which were all grown in Victoria. So there's 80 different varieties across 3 seasons and 4 different growing locations. So there's a fairly similar story to the mung beans in that there was some predictive power for antioxidant capacity in the cross-validation, but this fell within the test set, which means that the model that was created was really specific to those samples and couldn't be broadly applied to assess new samples with a high level of accuracy. And so it's a similar story for total phenolic content. So some predictive power in the cross-validation set, but not in the test set. So again, it's probably likely due to either the lower levels of these compounds or low range of antioxidant or phenolic contents, meaning that it's very hard to make any prediction. And another reason could be, again, interfering compounds, which are absorbing in the infrared region. So the only previous study which used mid-infrared spectroscopy to predict total phenolic content in chickpea had a very limited sample size, so only 36 compared to 97 in this study. And they also had no test set. So what they found, they reported that mid-infrared spectroscopy could predict TPC, the total phenolic content, using larger sample size in this study and test set. I found that we couldn't really predict the total phenolic content with any accuracy. So I would feel that this study might be over-optimistic due to its small sample size and high number of components. So that would be my explanation for the difference between this study and previous work in this area. So looking at all the crops, we found that infrared spectroscopy, in particular near-infrared spectroscopy, showed promise for predicting total phenolic content and antioxidant capacity, but only in selected crops. So fava bean and wheat, it seemed to perform quite well. And with larger samples, larger calibration sizes, more samples in the calibration, these models could potentially be applied for general use, quality assurance, screening purposes, which could then be used to support the sale of Australian pulses as health benefiting functional food crops. However, these results weren't broadly applicable, so we didn't find any predictive power in mung bean and chickpea crops, which indicates that the application of infrared spectroscopy to predict these analytes in pulse crops needs to be crop specific. So one model won't necessarily work for all crops. And the reason for this may be due to their lower levels of phenolics or antioxidants or lower range in these between samples, so less difference between samples, or it could be other interfering compounds, and that's something we're still looking into. So I'd like to finish up by thanking my supervisors, Dr. Manny Naker and Professor Kerry Walsh, of the Australian government for providing me with an RTP scholarship to do this work, and our industry partners who supplied the samples and other in-kind support. So Australian Export Grains Innovation Centre for the wheat, Agriventus Technologies for the fava beans and mung beans, and Agriculture Victoria for supplying the chickpea samples. So thank you very much for listening. Hope you found it interesting. And if you have any questions or your comments, or you're interested in potential collaborations in the future, please drop me an email. My email address is at the bottom of the screen here. Thank you very much.